A gravitational lens refers to a distribution of matter between a distant source and an observer, that is capable of bending the light from the source, as it travels towards the observer. This effect is known as gravitational lensing, and the amount of bending is one of the predictions of Albert Einstein's general theory of relativity. Although Orest Chwolson or Frantisek Klin are sometimes credited as being the first ones to discuss the effect in print, the effect is more commonly associated with Einstein, who published a more famous article on the subject in 1936. Fritz Zwicky posited in 1937 that the effect could allow galaxy clusters to act as gravitational lenses. It was not until 1979 that this effect was confirmed by observation of the so-called twin QSOS BS0957 plus 561. Description: unlike an optical lens, maximum bending occurs closest to, and minimum bending furthest from, the center of a gravitational lens. Consequently, a gravitational lens has no single focal point, but a focal line instead. If the source, the massive lensing object, and the observer lie in a straight line, the original light source will appear as a ring around the massive lensing object. If there is any misalignment, the observer will see an arc segment instead. This phenomenon was first mentioned in 1924 by the St. Petersburg physicist Orest Chwolson, and quantified by Albert Einstein in 1936. It is usually referred to in the literature as an Einstein ring, since Chwolson did not concern himself with the flux or radius of the ring image. More commonly, where the lensing mass is complex and does not cause a spherical distortion of spatio-time, the source will resemble partial arcs scattered around the lens. The observer may then see multiple distorted images of the same source. The number and shape of these depending upon the relative positions of the source, lens, and observer, and the shape of the gravitational well of the lensing object. There are three classes of gravitational lensing: 1. Strong lensing, where there are easily visible distortions such as the formation of Einstein rings, arcs, and multiple images. 2. Weak lensing, where the distortions of background sources are much smaller and can only be detected by analyzing large numbers of sources to find coherent distortions of only a few %. The lensing shows up statistically as a preferred stretching of the background objects perpendicular to the direction to the center of the lens. By measuring the shapes and orientations of large numbers of distant galaxies, their orientations can be averaged to measure the shear of the lensing field in any region. This, in turn, can be used to reconstruct the mass distribution in the area. In particular, the background distribution of dark matter can be reconstructed. Since galaxies are intrinsically elliptical and the weak gravitational lensing signal is small, a very large number of galaxies must be used in these surveys. These weak lensing surveys must carefully avoid a number of important sources of systematic error: the intrinsic shape of galaxies, the tendency of a camera's point spread function to distort the shape of a galaxy, and the tendency of atmospheric seeing to distort images must be understood and carefully accounted for. The results of these surveys are important for cosmological parameter estimation, to better understand and improve upon the lambda-CDM model, and to provide a consistency check on other cosmological observations. They may also provide an important future constraint on dark energy. 3. Microlensing, where no distortion in shape can be seen but the amount of light received from a background object changes in time. The lensing object may be stars in the Milky Way in one typical case, with the background source being stars in a remote galaxy, or, in another case, an even more distant quasar. The effect is small, such that even a galaxy with a mass more than 100 billion times that of the Sun will produce multiple images separated by only a few arcseconds. Galaxy clusters can produce separations of several arc-minutes. In both cases the galaxies and sources are quite distant, many hundreds of megapascs away from our galaxy. Gravitational lenses act equally on all kinds of electromagnetic radiation, not just visible light. Weak lensing effects are being studied for the cosmic microwave background as well as galaxy surveys. Strong lenses have been observed in radio and X-ray regimes as well. If a strong lens produces multiple images, there will be a relative time delay between two paths, that is, In one image the lensed object will be observed before the other image. History. Henry Cavendish in 1784 and Johann Georg von Salzner in 1801 had pointed out that Newtonian gravity predicts that starlight will bend around a massive object, as had already been supposed by Isaac Newton in 1704 in his famous Queries No. 1 in his book Optics. The same value as Salzner's was calculated by Einstein in 1911 based on the equivalence principle alone. However, Einstein noted in 1915 in the process of completing general relativity, that his 1911 result is only half of the correct value. Einstein became the first to calculate the correct value for light bending. The first observation of light deflection was performed by noting the change in position of stars as they passed near the Sun on the celestial sphere. The observations were performed in May 1919 by Arthur Eddington and his collaborators during a total solar eclipse, so that the stars near the Sun could be observed. Observations were made simultaneously in the cities of Sobral, Ceará, Brazil and in Sao Paulo, Toma copyright and Pro-NCIPE on the west coast of Africa. The result was considered spectacular news and made the front page of most major newspapers. It made Einstein and his theory of general relativity world famous. When asked by his assistant what his reaction would have been if general relativity had not been confirmed by Eddington and Dyson in 1919, Einstein famously made the quip, "Then I would feel sorry for the dear Lord." The theory is correct anyway. Space-time around a massive object is curved, and as a result light rays from a background source propagating through space-time are bent. The lensing effect can magnify and distort the image of the background source. According to general relativity, mass warps spatial-time to create gravitational fields and therefore bend light as a result. This theory was confirmed in 1919 during a solar eclipse, when Arthur Eddington and Frank Watson Dyson observed the light from stars passing close to the Sun was slightly bent, so that stars appeared slightly out of position. Einstein realized that it was also possible for astronomical objects to bend light, and that under the correct conditions, one would observe multiple images of a single source, called a gravitational lens or sometimes a gravitational mirage. However, as he only considered gravitational lensing by single stars, he concluded that the phenomenon would most likely remain unobserved for the foreseeable future. In 1937, Fritz Zwicky first considered the case where a galaxy could act as a source, something that according to his calculations should be well within the reach of observations. It was not until 1979 that the first gravitational lens would be discovered. It became known as the twin QSO since it initially looked like two identical quasistellar objects. It is officially named SBS 0957+561. This gravitational lens was discovered by Dennis Walsh, Bob Carswell, and Ray Wieman using the Kitt Peak National Observatory 2.1-meter telescope. In the 1980s, astronomers realized that the combination of CCD images and computers would allow the brightness of millions of stars to be measured each night. In a dense field, such as the galactic center or the Magellanic Clouds, many microlensing events per year could potentially be found. This led to efforts such as optical gravitational lensing experiment, or OGLE, that have characterized hundreds of such events. Explanation in terms of spatio-time curvature. In general relativity, light follows the curvature of space-time, hence when light passes around a massive object, it is bent. This means that the light from an object on the other side will be bent towards an observer's eye, just like an ordinary lens. Since light always moves at a constant speed, lensing changes the direction of the velocity of the light, but not the magnitude. Light rays are the boundary between the future, the space-like, and the past regions. The gravitational attraction can be viewed as the motion of undisturbed objects in a background curved geometry or alternatively as the response of objects to a force in a flat geometry. The angle of deflection is toward the mass m at a distance r from the affected radiation, where g is the universal constant of gravitation and c is the speed of light in a vacuum. Since the Schwarzschild radius is defined as, this can also be expressed in simple form as search for gravitational lenses. Most of the gravitational lenses in the past have been discovered accidentally. A search for gravitational lenses in the Northern Hemisphere, done in radio frequencies using the Very Large Array in New Mexico, led to the discovery of 22 new lensing systems, a major milestone. This has opened a whole new avenue for research ranging from finding very distant objects to finding values for cosmological parameters so we can understand the universe better. A similar search in the Southern Hemisphere would be a very good step towards complementing the Northern Hemisphere search as well as obtaining other objectives for study. If such a search is done using well-calibrated and well-parameterized instrument and data, a result similar to the Northern Survey can be expected. The use of the Australia Telescope 20 GHz survey data collected using the Australia Telescope Compact Array stands to be such a collection of data. As the data were collected using the same instrument maintaining a very stringent quality of data, we should expect to obtain good results from the search. The AT20G survey is a blind survey at 20 GHz frequency in the radio domain of the electromagnetic spectrum. Due to the high frequency used, the chances of finding gravitational lenses increases as the relative number of compact core objects are higher. This is important as the lensing is easier to detect and identify in simple objects compared to objects with complexity in them. This search involves the use of interferometric methods to identify candidates and follow them up at higher resolution to identify them. Full detail of the project is currently under works for publication. In a 2009 article on Science Daily, a team of scientists led by a cosmologist from the U.S. Department of Energy's Lawrence Berkeley National Laboratory has made major progress in extending the use of gravitational lensing to the study of much older and smaller structures than was previously possible by stating that weak gravitational lensing improves measurements of distant galaxies. Astronomers from the Max Planck Institute for Astronomy in Heidelberg, Germany, the results of which are accepted for publication on October 21, 2013 in the astrophysical journal Letters, discovered what at the time was the most distant gravitational lens galaxy termed as J1000+0221 using NASA unregistered trademark S Hubble Space Telescope. While it remains the most distant quad-image lensing galaxy known, an even more distant two-image lensing galaxy was subsequently discovered by an international team of astronomers using a combination of Hubble Space Telescope and Keck telescope imaging and spectroscopy. The discovery and analysis of the IRCO218 lens was published in the astrophysical journal Letters on June 23, 2014. A research published September 30, 2013 in the online edition of Physical Review Letters, led by McGill University in Montreal, Quay copyright Beck, Canada, has discovered the beam modes that are formed due to gravitational lensing effect, using National Science Foundation's South Pole Telescope and with help from the Herschel Space Observatory. This discovery would open the possibilities of testing the theories of how our universe originated. Solar gravitational lens. Albert Einstein predicted in 1936 that rays of light from the same direction that skirt the edges of the Sun would converge to a focal point approximately 542 AU from the Sun. Thus, the Sun could act as a gravitational lens for magnifying distant objects in a way that provides some flexibility in aiming, unlike the coincidence-based lens usage of more distant objects, such as intermediate galaxies. A probe's location could shift around as needed to select different targets relative to the Sun. This distance is far beyond the progress and equipment capabilities of space probes such as Voyager 1, and beyond the known planets and dwarf planets, though over thousands of years 90,377 SNA will move further away on its highly elliptical orbit. The high gain for potentially detecting signals through this lens, such as microwaves at the 21 cm hydrogen line, led to the suggestion by Frank Drake in the early days of SETI that a probe could be sent to this distance. A multi-purpose probe set a sail and later focal was proposed to the ESA in 1993, but is expected to be a difficult task. If a probe does pass 542 AU, the gain and image forming capabilities of the lens will continue to improve at further distances as the rays that come to a focus at these distances pass further away from the distortions of the Sun's corona. Measuring weak lensing, Kaiser et al., Lupino and Kaiser and Hoekstra et al. Prescribed a method to invert the effects of the point spread function smearing and shearing, recovering a shear estimator uncontaminated by the systematic distortion of the PSF. This method is the most widely used method in current weak lensing shear measurements. Galaxies have random rotations and inclinations. As a result, the shear effects in weak lensing need to be determined by statistically preferred orientations. The primary source of error in lensing measurement is due to the convolution of the PSF with the lensed image. The Ksb method measures the ellipticity of a galaxy image. The shear is proportional to the ellipticity. The objects in lensed images are parameterized according to their weighted quadrupole moments. For a perfect ellipse, the weighted quadrupole moments are related to the weighted ellipticity. Ksb calculate how a weighted ellipticity measure is related to the shear and use the same formalism to remove the effects of the PSF. Ksb a unregistered trademark's primary advantages are its mathematical ease and relatively simple implementation. However, Ksb is based on a key assumption that the PSF is circular with an anisotropic distortion. Unregistered trademark's fine for current cosmic shear surveys, but the next generation of surveys may need much better accuracy than Ksb can provide. Because during that time, the statistical errors from the data are negligible, the systematic errors will dominate. Gallery. See also, Einstein cross, Einstein ring, SN Rifstall. Historical papers and references, Chwolson, O. Adbrain mar paragraph gleich vom fiktive Doppelsten. Astronomische Nachrichten 221, 329. Bibcode, 1924 AN, 221 329 C doi, 10.1002/ASNA 19,242,212,003. Einstein, Albert. Lens-like action of a star by the deviation of light in the gravitational field. Science 84, 506 7. Bibcode, 1936 Sci, 84506 doi, 10.1126/Science. 84.21 88.506. JSTOR 1,663,250. PMID 17,769,014. Reen, JAR 1/4 GEN. Tillman Sauer. John Stackel. The Origin of Gravitational Lensing, a postscript to Einstein's 1936 science paper. Science 275, 184 6. Bibcode, 1997 Sci. 275 184 doi, 10.1126/Science. 275.52 97.184. PMID 8,985,006. References, Notes. Bibliography, Accidental Astrophysicists. Science News, June 13, 2008. Ksb lenses. A computer program to visualize gravitational lenses, Francisco Frutos Alfaro, G-Lens. A point mass gravitational lens simulation, Mark Buffon. Newbury, Pete, Gravitational Lensing. Institute of Applied Mathematics, The University of British Columbia. Cohen, N., Gravity's Lens, Views of the New Cosmology, Wiley & Sons, 1988. Q0957 plus 561 Gravitational Lens. Harvard.edu. Gravitational Lensing. gsfc.nasa.gov. Bridges, Andrew, Most Distant Known Object in Universe Discovered. Associated Press. February 15, 2004. Analyzing Corporations and the Cosmos, an Unusual Career Path in Gravitational Lensing. HST Images of Strong Gravitational Lenses. Harvard-Smithsonian Center for Astrophysics. A Planetary Microlensing Event, and a Jovian Mass Planet in Microlensing Event OGL 2005 BLG071, the first extrasolar planet detections using microlensing. Gravitational Lensing on arXiv.org, NRAO class homepage, 8020G survey, a diffraction limit on the gravitational lens effect, further reading, Blandford and Narayan. Narayan, R. Cosmological applications of gravitational lensing. ARA and A30, 311 Euro 358. Bibcode, 1992 ARA and A30 311B DOI, 10.1146/An Yuri Vor. 30.090192.001523. Matthias Bartelmann and Peter Schneider. Weak gravitational lensing. Kavinson, Dmitry. Newman, Ginevra. From Fundamental Theorem of Algebra to Astrophysics, A Harmonious Path. Notices 55, 666 Euro 675. Peters, Alio. Levine, Harold. Wombs-Gantz, Joachim. Singularity Theory and Gravitational Lensing. Progress in Mathematical Physics 21. Berger Currency User. Tools for the evaluation of the possibilities of using parallax measurements of gravitationally lensed sources. External links, video, Evelyn Gates Euro Einstein's Telescope, The Search for Dark Matter and Dark Energy in the Universe, presentation in Portland, Oregon, on April 19, 2009, from the author's recent book tour. Audio, Fraser Cain and Dr. Pamela Gay Euro Astronomy Cast, Gravitational Lensing, May 2007. Featured in Science Fiction Works, Existence, by David Brin, 2012.